Hi, a couple words on torque. You'll notice on the equation sheet that there are different forms of the equation for torque. So first we have torque as a vector equals R cross F, and then in terms of magnitude that translates into torque equals R F sine of the angle. Alright, so there are two other expressions which I'm going to explain right now. So if you look at R and an F, okay, so there's an R and there's an F, and there's some angle between the R and the F. If you notice, if you look at the components of F, there's a component parallel to that line and a component perpendicular to that line, which is the one I want to point out. So that component is F sine of theta. So what that means is that torque equals R F sine of theta can be written as torque equals R F perpendicular. What that is the component of F that is perpendicular to the vector R. Because F sine of theta is F perpendicular. So the component of F perpendicular to the R vector. So R as a distance is there, R as a vector points away from the pivot point and keeps on going. So what does that mean? That means basically if you take the component of F that is perpendicular to the R, that's the one that causes the torque. So basically we could write this as R and then F perpendicular here. So the real F is like that, but the part that matters is the part that's perpendicular to R. That is the part that actually makes it go in this circular direction. The part that's parallel to R doesn't really apply any torque. It's going in that direction. It doesn't do anything. So that is the expression torque equals R F perpendicular. Now the other expression we can see if we draw an R and an F. Let's make it kind of like, let's see, maybe kind of like that, with some angle in between them. And here what we're going to want to do is extend the line of F, and if we draw a line from the pivot point to this line so that it's perpendicular, we can look at the angles and we can see that this angle is the same as that angle, so that this length here is R sine of theta. And this R sine of theta is, we call this R perpendicular. That is, it is the component of R that's perpendicular to the line of F. You know, to the line that goes through the vector F. So our expression torque equals R F sine of theta can be written, if we take the R sine of theta and put it together, torque equals R perpendicular F. So that is, so R perpendicular, which is often called the lever arm, is the distance from the pivot point to the line that is parallel to F. So that's going to look like this. Torque equals R perpendicular F. So which one should you use? Well, they're all kind of useful in different situations. You can always use this one, torque equals R F sine of theta. It's just that sometimes some of these might be more visual and easier to see. So let's look at a couple examples. If we have a beam supported by a wire, so there's various torques in this problem, but the one I'm going to look at here is the torque caused by the tension, and if we're given this angle. So now here, the torque caused by the tension is going to be RF. So R is the length of the beam, and then F is the tension itself. So if that's the length of the beam, so then the torque caused by the tension, say, is L times T times sine of the angle. And what angle would that be? that would be this angle. There. So that's possible to do. It's really not a big problem to get that angle. If you know this, you can figure it out. Not too hard at all. However, what we tend to do in this case is we use this expression, torque equals Rf perpendicular. And we look at the component of the force, the component of the tension that is perpendicular to the beam, perpendicular to the R. So that's going to be quite helpful. So in fact, this angle is equal to this angle. So T perpendicular is T cosine of theta. So the point is, in some cases it's easier just to do that than just try to find that whole angle. Not only is it easier, but it's a little more visual because we're going to need, I'll call it Ty, we're going to need Ty and Tx to solve the rest of the problem, as you'll see. So if you have this component there, you might as well use it. So it's basically R times F. So that's one example where it's convenient to use Rf perpendicular. In another example, where you have like a ladder against the wall. Alright, so if we consider the mass of the ladder here, so there's a force going down mg. The length of the ladder is L, so each half of it is L over 2. I'm just giving a brief example. So if we use, we'll go through the problem later, but for now, I won't explain why, but if this is our pivot point, then we're considering how this force causes a torque around that pivot point, like that. So the torque is R, which is L over 2, times mg, times sine of the angle. And so again, that's going to be a big angle. It's going to be this whole angle here. So why bother with that when you could just use the lever arm approach? If you have a straight shot from here to the line of the force, might as well use that. So instead of saying L over 2 mg sine of the big angle, we can say torque equals R perpendicular F. R perpendicular is going to be this. So if you happen to know this angle, that's helpful. So L over 2 cosine of theta, and then the F is mg. So this becomes the lever arm. So let me draw it in here. There you go. L over 2 cosine of theta. So that's the distance from the pivot point to the line of the force. So many times that becomes easier to deal with than finding the whole angle. So you can use whatever you want, but if you get used to using these, you'll find that it's kind of easier to get right at the expression that you need quickly without thinking about angles too much. So those are the three expressions for torque.